Now that we have the theoretical result, we will see it as an application for quantum computers thanks to the services offered by IBM with access to real quantum computers.
Exactly. Let's see some real-life results. These results are proof that this phenomenon can be experienced in the real world and not only theoretically. You can see the quantum circuit that we will use. It is slightly different from the one presented so far, so let's dig into it. First, we have the three qubits used for the protocol and three classical bits that will allow us to store a measured result and prove the teleportation went as we wanted.
First, we initialize the different states and entangle Alice and Bob's qubit with Hadamard followed by CNOT gates. We can run the calculations as follows, starting with the initial state which is the same as before. Now we will adapt the circuits to the detector we have, which measures in the computational basis. To do so, we used the CNOT gate between Alice and the state we want to teleport Omega. The system is now in this state. We then use a Hadamard gate on the quantum state Omega and obtain this new state. We have the same result as before, but now expressed in the computational basis. However, we face a problem. In fact, to accomplish the protocol, we need to retrieve the measurement of Alice's two qubits and communicate the result to Bob in order to put the appropriate gate as we have seen before. This method needs to be adapted to the quantum computer. The classical communication between Alice and Bob has to be written differently to still perform the protocol. To do so, we need a little bit more of calculations with the final part of this quantum circuit.
Indeed, if we make the same reasoning as before in the computational basis, when Alice measures the state and a qubit, if she obtains 00, Bob will perform an identity transformation. If she obtains 01, it is a X gate, 10 a Z gate, and finally 11 a X and then a Z gate. Thus, by analyzing those results, we can see that when the qubit C is excited, meaning in the state 1, Bob needs to apply a Z gate, and when it is Alice qubit, Bob applies a NOT gate. From this analysis, we can deduce we need a CNOT gate with Alice qubit as the controlling qubit and a controlling Z gate with the quantum state as the controlling qubit. Fortunately, those operations can be performed using IBM programming language. We finally can perform a measurement on Bob's qubit to verify the information has indeed been teleported. Now we have a new circuit that can imitate the result of the theoretical teleportation protocol. Obviously, this circuit is of non-use in real-life communication application because in order to perform a controlled gate, the two qubits must be close. However, it is of great use in quantum computing.
Now that we have the modified circuit for IBM's quantum computer, we can perform the algorithm on simulators and compare to real quantum computers thanks to the services provided by IBM. Here we are on the IBM Q experience that offers an interface where we can run and build quantum algorithms. On the Quantum Lab, we can code the algorithm in Qiskit, a Python library to design and execute quantum circuits on IBM services. So here we have imported Qiskit and the IBM account that will allow us to run the circuit on real quantum computers. Then, on this cell, we create and initialize the circuit. We have the different qubits Omega that will be teleported, Alice, and Bob. And finally, a classical register for Bob. In fact, to know we have the state Omega in the end, we will measure Bob's qubit several times to obtain a good approximation of the probabilities of the states to be either 0 or 1. In the state initialization, we will encode this particular state, square root of 2 over 3 and square root of 1 over 3, which is a superposition of states 0 and 1. Thus, to verify the teleportation is correct, we need to obtain the probabilities 2 over 3 for state 0 and 1 over 3 for state 1 as we measure it several times. Here, we create the circuits we presented before, and we can finally obtain the results by executing the circuits on the simulator 124 times. We obtain the following results as histograms. The results show the probabilities of a box qubit to be either 0 or 1, which matches quite well the initialization we made, as we have 0.658 and 0.342. We have teleported, indeed, the information encoded in the qubit omega onto Bob's qubit. Now that the simulation is quite correct, we can run the code on real quantum computers. We use the IBM Santiago to run the quantum algorithm that we made on the quantum computer. As the services are quite busy, we need to wait before we obtain the results, and the job will appear here as pending. We will get back when the job will be done, and we can plot the histogram of the results that we obtain with the real quantum computer. So here we can see that the job is finally done, and we can plot the results. We can see that we also obtain probabilities that matches the expectation, because we have something that is close to 2 over 3 for state 0 and 1 over 3 for state 1. And we have finally teleported the qubit omega on Bob's qubit using the real quantum computer. Amazing, right?